Okay, today we're going to see how the Laplace transform can be used to help us solve initial value problems. So this is 7.2 in the textbook and then section 4.2 in my notes covering that same material. I've just posted the homework for section 7.2 and it will be due on Monday, April 27th, and then there'll only be one more homework after that. Um, So how we can use Laplace transform is by a simple rule that allows us to take the Laplace transform of the derivative of a function. Um, so what I'll show you here is suppose I want to compute the Laplace transform of f prime of t. So I'm going to assume that I already know the Laplace transform of f of t. What is the transform of f prime? So if I use the definition of Laplace transform, that's the integral from 0 to infinity of e to the minus st f prime of t dt, and the result of this will be a function of s. Um, so now, what I will do with this integral is use integration by parts. Now remember, in integration by parts, you break this integrand up into u and dv, and u should be something easy to differentiate, like an exponential. dv should be something that's easy to integrate. Well, a derivative itself is easy to integrate. So if dv is f prime, then v would be equal to f. So integration by parts would give me um, u, which is e to the minus st, times v, which is f of t, with limits 0 and infinity. And then I have minus the integral of v, which is f of t, times du. Well, du is a derivative of this part, which is vu. So it would be minus s e to the minus st. So I'll fill in e to the minus st. And um, so since the derivative is minus s e to the minus st, that will give me a plus and then a factor of s. Now, s I'm allowed to pull outside the integral because the integral is with respect to t. Okay. Now, um, in this part here, if I let t go to infinity, e to the minus st will go to 0. So plugging in infinity will give me nothing. When I plug in t equals 0, well, e to the 0 will be 1, and then what's left is just f of 0. But that's the lower limit, so it gets a minus. And then over here, this integral is exactly the Laplace transform of f. Notice these two integrals exactly the same, except here we have f prime, here we have f. Um, so that will give me s times the Laplace transform of f of t, which can also be written as s f of s minus f of 0, um, where Laplace transform of f of t. So this is how the Laplace transform of a derivative can easily be expressed in terms of the Laplace transform of the original function. You multiply by s and subtract off f of 0. So this is very convenient for initial value problems. Suppose we have y prime in a differential equation. Then you transform the equation, you would get s capital Y of s, so Laplace transform of a solution, minus the initial value. So this rule for a derivative makes it easy to take into account initial conditions of a dE, at least if the initial time is 0. If it's not 0, then you can always do some change of variable and shift it so it is 0. Now, I won't derive it here, but we have a similar rule for Laplace transform of a second derivative. So all I would do is, if I take a Laplace transform of f double prime using a definition, I would still go through this process. I would just have to carry out integration by parts twice. So I would get s squared f of s, which is predictable because it's second derivative. And when I subtract off f prime of 0, and then I subtract off minus s f of 0. So in general, nth derivative, you have s to the n times the Laplace transform of the original function. And when you're subtracting off all the values of the function n's derivatives at 0, so if it's the nth derivative, then n minus first derivative would have no factor of s. And as you go down the order of derivatives, the power of s increases. For our purposes, we're just going to be working with first and second derivatives. So these two rules here are the only ones that we will need. The general rule for nth derivative is stated in the notes, however. So now we're ready to use what we know about Laplace transforms to solve initial value problems. So I have several examples I'm going to work through. All right, so the initial value problem is, okay, so y double prime minus 5y prime plus 6y is equal to 0, and initial conditions, y0 is 1, y prime is 0, equal minus 1. Okay, so the first thing you do is to take a Laplace transform of both sides of the equation. And we'll use the initial values along the way. So now the right side, the Laplace transform of 0 would just be 0. On the left side, we're going to have Laplace transform of y double prime. So that would be s squared. And you can use capital Y of s to refer to the Laplace transform of y of t. So minus y prime 0 minus sy of 0. All right, so that's y double prime. That took care of this. Now I move to minus 5 y prime, so that would be sy of s minus y of 0 plus 6 capital Y of s. So that is the Laplace transform of the differential equation. Now, so unlike what you're used to from solving these kind of equations, used to be you would take the initial conditions into account only at the very, very end. Here we do it pretty much at the very beginning. So I'm just going to duplicate this and fill in the initial values. So y prime of 0 is minus 1, so that would give me a plus 1 here. And then y of 0 is equal to 1, so I'll fill that in. Okay. Now, the next thing is we're going to solve for y of s, because that is the Laplace transform of our solution y of t. I'll just remind you that that's what capital Y of s is, Laplace transform of our solution. Now, how do you do that? We need to rearrange these terms. So any term involving capital Y of s, we need to group all of those terms together. So I have s squared y of s, and then minus 5y of s, and then or 5sy of s, and then 6y of s. So I'm going to get s squared minus 5s plus 6 all times y of s. Okay. And then after that, I will write whatever other terms we have. So I have plus 1 minus s coming from here, and then I have plus 5, and then that's it. All that is equal to 0. Now, any terms not involving y of s, we move them to the other side. So now I have s squared minus 5s plus 6 y of s is equal to, so this combines to 6 minus s. I move it to the other side, so I have s minus 6. And then we just go ahead and divide. So this is how it works every time. even if it's a non-homogeneous DE, which we'll see toward the end of this lecture, we'd have something over here. But whatever terms we get that are not multiplying y of s, get them all on the right side, wherever they come from. So our Laplace transform of our solution is s minus 6 over s squared minus 5s plus 6. All right, and this goes to the point that I made at the end of last class, that the nice thing about a Laplace transform, or one of the nice things, besides the fact that it makes it easy to take into account initial values, is that it transforms a differential equation, like this one, into an algebraic equation, this one. From here to here, we just did algebra to get to Laplace transform of a solution. But now we could say this is where the hard part begins, because we still need little y of t. That's the solution of our original problem. So we need to carry out the inverse transform. All right. So I'll go ahead and walk you through that process, and then we'll continue this with more examples. So I'm going to continue this onto a new page. If it'll let me. Okay. Now, one thing that is a good idea to do with an expression like this is factor the denominator, and then also from what you would have seen in Calculus 2, partial fraction decomposition to break this up into fractions that are easier to work with from an inverse transform point of view. In Cal 2, you did it to integrate. Here again, we want simpler expressions to work with. So if I go ahead and factor the denominator, so that would be s minus 6 over s minus 2 times s minus 3. So those are factors of s squared minus 5s plus 6. One thing I want to point out is this factor multiplying y of s up here, you can always read it right off the DE. It's like a characteristic equation. The characteristic equation of this equation is s squared minus 5s plus 6 is equal to 0. So whatever you get from a characteristic equation, you'll have the exact same polynomial multiplying y of s. It always works that way, just because of how Laplace transforms of derivatives work. First derivative gives you an s, second derivative gives you an s squared, just like in a characteristic equation. Okay, so now we're here, and the partial fraction decomposition of this is equal to some constant a over s minus 2 plus another constant b over s minus 3. So now we need to figure out what a and b are. This is kind of a review of what you would have learned in Cal 2. So what you can do is, if you multiply both sides by the denominator, s minus 2 times s minus 3, then on the left side we'll just have a numerator left, s minus 6. And then on the right side, I'm going to have all of this times s minus 2 and s minus 3. The s minus 2 terms will cancel. So I'll have s minus 3. And then in the b term, the s minus 3 factors will cancel. So what I did here was multiply through by s minus 2, s minus 3. Okay. All right. And after simplifying, this is what you get. So it's always going to be each constant times whatever other factors you have. So you can jump directly to this. So keep that in mind. Now, what is called by calculus books method of creating zeros. You can substitute any two distinct values of s in here and get equations for a and b. But we might also substitute the s values that make these two equations easiest to solve. You substitute s values that make factors 0. So in this case, it would be s equals 2 to get A, and then s equals 3 to get B. So if I substitute s equals 2, so I'll get 2 minus 6, that's minus 4, is equal to A times 2 minus 3. And then I plug in s equal 2 here, I'll get 0. So what that gives us is minus 4 equals minus A, so A is equal to 4. And then similarly, s equals 3, I'll get 3 minus 6, so minus 3 on the left. And then I plug in s equals 3, this term will go away, and then I'll have B times 3 minus 2. So what we get from that is 1 times B is equal to minus 3, so B is equal to minus 3. Okay, so now the Laplace transform of our solution can be written as 4 times 1 over s minus 2 minus 3 times 1 over s minus 3. All right, so now we need to take the Laplace transform of the inverse transform of both sides. So y of t, which is the inverse transform of y of s. Now, just as the Laplace transform is linear, the inverse transform is also linear. So you get 4 times the inverse transform of 1 over s minus 2 minus 3 times the inverse transform of 1 over s minus 3. Okay. Now, so once we know how to work out these inverse transforms, we'll be done. So a transform that we saw previously is that the Laplace transform of e to the at, that is equal to 1 over s minus a, which is the same kind of expression that we see here for a equal 2 or 3. But that is the same, that's equivalent to saying that the inverse transform of 1 over s minus a is e to the at. So the door swings both ways. So any function you know how to transform, you automatically know some inverse transform. In this case, this one. So what we have is y of t would be equal to 4 times this inverse transform with a equal to 2, so that would give e to the 2t, and then minus 3 times the inverse transform of 1 over s minus 3. So it's this inverse transform with a equal to 3, so that'd be e to the 3t. And then we're done. So that's how the process works, is you take the transform of a differential equation using rules for derivatives, and that's when you'll take the initial values into account. And all the homework problems, initial values will be provided. Then you do some algebra to solve for the Laplace transform of a solution, and then you get the transform of a solution into a form where you can readily inverse transform it. That will often involve partial fraction decomposition, for example. Other examples I'll show you in a little bit will involve other algebraic techniques. So I'll bring you up to speed on all of those. Once you have it in this kind of form, where basically you want to compare to a Laplace transform table. Now, Laplace transform table gives you transforms and inverse transforms, even if it doesn't explicitly write it that way. A function of, so you can take a function of t and take a Laplace transform of it to get a function of s, or you can take a function of s and go backwards, so basically like right to left in most tables, to take the inverse transform of a function of s to get the corresponding function of t. Okay, so that's one example. Now I'll show you another that involves somewhat different algebra. Um, so before getting into that example, all right, so that box will mark the end of this example. So one Laplace transform that will be very useful to us is that the Laplace transform of e to the at times some function of t, based on the definition, that would be equal to e to the minus st, e to the at, ft. But I can combine these exponentials. So that would be e to the minus st plus at, add the exponents. But that'd be the same thing as saying e to the minus s minus a times t. So now you're taking a Laplace transform of just plain old f. But instead of evaluating that Laplace transform at s, it'll just be s minus a, because this is the definition of Laplace transform, just that s is replaced by s minus a. Now this is a generalization of what we saw here. Like basically, if you take this rule with f of t equal to 1, you get exactly this. What's the Laplace transform of 1? It's 1 over s. So Laplace transform e to the at would be 1 over s shifted, s is replaced by s minus a. So more generally, if you're taking a Laplace transform of any function f of t, multiplied by an exponential, the effect of the exponential is to shift the Laplace transform of little f of t. So that's going to be helpful to us in inverse transforming in examples. Okay. Now, so for the next example, our initial value problem will be y double prime plus 4y prime plus 4y is equal to 0. These initial conditions, y is 0 equals minus 2, y prime of 0 equal 1. Okay. So we go ahead and take the transform, and what that gives us is, for second derivative, s squared y of s minus y prime of 0, which is 1, and then minus s times y of 0, which is minus 2, so that'll actually give me a plus 2s. And then I have plus 4 Laplace transform of y prime, so that's going to be s y of s minus y of 0, which is, so minus a minus 2, so that'll give me a plus 2. Okay, and then plus 4y of s is equal to 0. So, so remember, second derivative, s squared y of s, subtract off the y prime, and then subtract off y of 0 times s for second derivative. First derivative, it's sy of s, subtract off y of 0. So that's where these terms come from. Right. Okay, so now I'm going to group all the terms involving capital Y of s together. So that would be y of s multiplied by s squared, and then 4s then 4. And then all other terms go to the other side. So I have minus 1, moving it becomes plus 1. I have minus 2s, that's being moved to the other side. And then here I have plus 8, moved to the other side is going to be minus 8. So now I can combine these terms. 1 minus 8 will give me minus 7. Okay. So now I have Laplace transform my solution. So that would be minus 2s minus 7 over s squared plus 4s plus 4. Okay. Now, we want to get this into a form that we can easily take the inverse Laplace transform. And to do that, it's a good idea to see how this factors, what are its roots. This happens to be a perfect square. It factors into s plus 2 quantity squared. So I'm going to write it this way. Minus 2s minus 7 over s plus 2 quantity squared. All right. Now, in this case, instead of doing partial fractions, I'm going to use some trickery to write the numerator as a function not of s, but of s plus 2. That'll allow me to break this up into the simplest fractions possible as far as inverse transforming is concerned. 2s minus 7 as a function of s plus 2. So how do you do that? So you have 2s minus 7. What you do is to introduce an s plus 2, I'm going to replace s with s plus 2 minus 2. All right, so right here, I haven't really changed anything. I've just added and subtracted a 2. But then I want to group s plus 2 together. So this s and this plus 2 must stay together. Now I can go ahead and do some distributing. So I have minus 2 s plus 2, and then I have minus 2 times minus 2 is plus 4, and then I still have this minus 7 here. So now I have minus 2 s plus 2 minus 3. Okay. So that's how you can write a function in shifted form. Just add and subtract the shift, and then be sure to keep your variable and the appropriate shift, keep them together as you distribute and combine terms. So now I have y of s equal to minus 2 s plus 2 minus 3 over s plus 2 squared. And now what I will do is break this up into two fractions. All right, so for first fraction, I'll have minus 2 s plus 2, and then I'll have s plus 2 squared down below. And then the other fraction will have minus 3 up top, and then s plus 2 squared below. Now, in the first fraction, I can cancel one of the s plus 2's. So I'll have minus 2 over s plus 2 to a first power now, and then this other fraction. Okay. So this will be much easier to work with as far as inverse transforms are concerned. So here are the transform rules that I will use. Whoops. So Laplace transform of 1 is 1 over s. Laplace transform of t is 1 over s squared. Here we have functions similar to 1 over s and 1 over s squared. It's just that they're shifted. But the way we could deal with that is using this third rule, Laplace transform of, as we just saw a little while ago, e to the at ft is equal to capital F of s minus a, where capital F is the Laplace transform of little f. So if we use these together, what we'll have is minus 2 times the inverse transform of one over s plus 2 plus, I should say minus 3 times the inverse transform of 1 over s plus 2 squared. Okay. Now, so what we have in both cases are shifted functions. So here we have capital F of s minus a, where a is equal to minus 2, and capital F in this case is 1 over s. Here we have a again equal to minus 2, and capital F would be equal to 1 over s squared. So if I take the inverse transform of 1 over s, that'll be equal to 1. But then the shift gives a factor of e to the minus 2t. And then I have minus 3. And here, the inverse transform of 1 over s squared would be t, but the shift of plus 2 right here, so really the value of a is minus 2, would give me t times e to the minus 2t. Okay, I'm going to fill in an intermediate step. So that's the same as saying e to the minus 2t times, hope I can fit this all in one line, the inverse transform of 1 over s, and then in the other term we have the inverse transform of 1 over s squared. So if you look at what's going on here, to go from here to here, I'm accounting for the shift up front. Here I have a shifted function of s plus 2. That's going to cause an e to the minus 2t factor in both cases. And then what we're left inverse transform is the unshifted function. So 1 over s plus 2 becomes 1 over s. 1 over s plus 2 squared becomes 1 over s squared. And then we inverse transform those functions that are simpler, and we get 1 over s transforms back to 1. 1 over s squared transforms back to t, causing this factor of t right here. And then we're done. We have our solution. All right, so that's our second example done. So, so watch for these shifted functions that. So it's a situation like this where you just have a denominator with some single factor raised to a power. You can write the numerator in terms of the same shift in order to get simpler fractions to work with. And always remember, inverse transform of 1 over s is 1. Inverse transform of 1 over s squared is t. And we're going to be making frequent use of this, that anytime you have a shifted function to transform back, that leads to multiplying the inverse transform of the unshifted function, like 1 or t, by an exponential. Okay, so now we'll move to our third example. So our initial value problem will be y double prime plus 6y prime plus 10y I just realized there's a typo in the notes. I forgot the y in this term. So I'll fix that. So y of 0 is, I'm just going to leave it initialized generic in this case. So y is 0 is y naught, y prime is 0 will be called z naught. Okay. So we go ahead and take the transform. And that gives us, for second derivative, we have s squared y of s minus y prime, that's z naught, and then minus s y naught, okay, plus 6 times the transform of first derivative, so that'd be s y of s minus the initial values, that's y naught, plus 10 capital Y of s, and that equals 0. Okay. Then, as before, we rearrange, group all the capital Y of s terms together, and we get s squared times y of s plus 6x, 6s, s, not x, s, 6s y of s plus 10 times y of s. And then we have these other terms that are moved to the other side. So I have z naught that gets moved to the other side. And then I have minus sy naught, but that becomes plus sy naught on the right side. And then I have minus 6y naught, but that gets moved to the other side too. So I'll have s plus 6y naught plus z naught. Okay, and then I go ahead and divide. So now I have Laplace transform of my solution. So that's going to be s plus 6 y naught plus z naught all over s squared plus 6s plus 10. Okay. All right. Now, if you were to try to factor this polynomial, this quadratic down below, 6s squared plus 6s plus 10, you would find that you could not factor it nicely. It actually has complex roots. So if you would use a quadratic formula, s squared plus 6s plus 10, so the roots are minus 3 plus or minus I. So you would get those from a quadratic formula. So what you can do is complete the square to provide a form that will help us for inverse transforming purposes. S squared plus 6s plus 10 can be written as s squared plus 6s plus 9 plus 1. And so this part, s squared plus 6s plus 9, that is actually a perfect square. So that's equal to s plus 3 quantity squared plus 1. So once you have the roots using a quadratic formula, if you go that way, what you're always going to have here is minus the real part in the square, and then the imaginary part squared is going to go here. So in general, so complex roots s is equal to alpha plus or minus I beta. What you can do is write that the s squared plus okay, so the sum of the roots is going to be 2 alpha. Okay, so really that's minus there. And then the constant coefficient is always going to be the real part squared plus the imaginary part squared. So that can always be written as s minus alpha squared plus beta squared. So if you get the complex roots by quadratic formula, then you can put minus the real part here, and then the imaginary part squared goes here. So this is a form that we will use for purpose of taking the inverse transform. Okay. Now, so I want to take this numerator here and write it in terms of a shift. So capital Y of S is equal to S plus 6 Y naught plus Z naught over, and I'll use a square completed form down here, S plus 3 squared plus 1. Now, I could use the same trick as I did last time, so I could write this as S plus 3 minus 3. So if I go ahead and do that, all right, so I have S plus 3 minus 3. So then I can break it up like that. So S plus 3 goes here, minus 3 plus 6 goes here. And then minus 3 plus 6, that becomes a plus 3. Another way of looking at it is, I could just take this 6 and break it up into 3 plus 3. So I have S plus 3 Y naught, and then the rest of it is 3 Y naught. That goes over here. And that's so I can work with separate fractions here. So I have, so for the first fraction, I have S plus 3 up top, and I have S plus 3 squared plus 1 down below. And then Y naught is a constant factor I'm going to put off to the side. And then for the uh, other factor, I'm going to have 3 Y naught plus Z naught times 1 over S plus 3 squared plus 1. Okay. So the idea is I want the whatever shifted S factor I have down below, I want the same up top if there's any for any linear term involving S, or a constant. So both of these would be easy enough to transform back. So here are the transforms that we're going to need. They're a little different from the last example. So we need so a transform of cosine of bt, where b is a constant, that is equal to s over s squared plus b squared. Similarly, transform of sine bt has a similar form, where we would have b over s squared plus b squared. And then we need this one that was also needed in the previous example, we needed most of the time, is dealing with an exponential, EVAT FT causes a shift. Right. Okay, so so I want to try to get these here to fit these formulas exactly. So what I have is y of t, which is the inverse transform of all of this. But that's going to be y naught times the inverse transform of that fraction that's being multiplied by y naught. So I'll just copy that. Okay. Plus, I need to make those brackets bigger. Okay. Plus this constant factor, free y naught plus z naught. Remember, constant factors could just be like set aside. Times the inverse transform of this fraction Okay. So now the next thing I want to do is take into account the shift. The shift in both cases is going to be a is equal to minus 3, leading to a s minus a is s plus 3. So I can have y naught e to the minus 3t times the inverse transform of s over s squared plus 1. So that's the unshifted version of this. Okay, plus 3y naught plus z naught times the exponential, e to the minus 3t again, minus 3t, okay, times the inverse um, inverse transform of this unshifted fraction, so 1 over s squared plus 1. Okay. All right, so now these fractions fit these formulas exactly. So I have y naught e to the minus 3t. Inverse transform of this, if it's this formula, would be equal to 1. So it's going to be cosine t. And then this one fits this formula, again with b equal to 1. So we get sine t. And we're done. We have our solution. Now, one cautionary tale for problems like this, where the numbers may be a bit different, is suppose instead of, for example, instead of plus 1 here, I had plus 4. So then my unshifted function would be 1 over s squared plus 4. Well, 1 over s squared plus 4, you think, oh, it fits this with b equal to 2. Well, no, it doesn't, because you must have a b up here. So it would fit exactly 2 over s squared plus 4. So what do? You multiply and divide by 2. So beware of this constant factor up here for inverse transforming to get sine. So when you have an expression like this, like after you've dealt with a shift, you try to match it against some transform, so you can take the inverse transform. Make sure it matches exactly. So this constant factor can get you. So you've been warned. Again, make sure that all parts of the formula fit before you apply it. And it's not hard to deal with in this case. You just have to just don't gloss over it. Okay. All right, so that's my third example. And I have one more. This one's going to be inhomogeneous problem. So I have y double prime minus 2y prime plus y is equal to e to the 2t. And initial conditions, y is 0 equal 1, y prime of 0 equal minus 1. Okay. So when you take the transform, you get s squared, capital Y of s, okay, minus y prime value. So that's going to be plus 1. Okay. And then minus s times y of 0. So it's minus s right there. And then I have minus 2 times the transform of y prime. That's going to be sy of s. minus the initial value, so that's minus 1, okay, plus capital Y of S is equal to the Laplace transform of e to the 2t. So remember, transform both sides. So what's the Laplace transform of e to the at? Well, it's this formula with f of t equal to 1. So you take the Laplace transform of 1 to get capital F, and that would be 1 over s. And then you shift it. So s becomes s minus a, where a is the coefficient of the exponential. So in this case, we have e to the 2t. So the simpler form of it is, let's see, where is it? This rule right here, transform of e to the 2t is 1 over s minus 2. So that's what we'll have on the right side. Okay, get down to the bottom here. 1 over s minus 2. Since Laplace transform of e to the at is something you need to basically commit to memory because you use it that often for these kind of problems. So that's 1. So as before, we rearrange. So I'm going to have anything multiplying capital Y of s, s squared minus 2s plus 1. And then on the right side, I'm going to have 1 over s minus 2 from before. And then any other terms will also move to the other side. So I have a minus s, that'll be moved over. So I'm going to have a plus s over here. And then I have a minus 1 that's moving over, so that'll become a plus 1. And then I have plus 2 over here. That will actually, something seems off in my notes here. Okay, hopefully it's not a mistake. Minus 1. Okay. Oh, yeah, I see where I messed up. All right, plus 1 over here is a minus 1 over here. Okay. If I have plus 2 over here, becomes a minus 2 over here. So I'm going to have minus 1, minus 2. We'll combine those terms, and we'll get s minus 3. So now, so y of s will turn out to be equal to s minus 3 over s squared minus 2s plus 1. And then I'll have 1 over s minus 2 times s squared minus 2s plus 1. And I see that I have a typo over there. Okay. So that's the Laplace transform of my solution. Now, as far as inverse transforming, of course, the first thing I want to do is gonna feel for a factorization of this quadratic, s squared minus 2s plus 1. This is actually a perfect square. Again, I'll continue this onto a new page. Excuse me. Alright, so y of s that'll be equal to s minus 3 over s minus 1 squared plus 1 over s minus 2, s minus 1 squared. Okay. So what I'm going to do next is put everything over a common denominator. So I'm going to throw in a factor of s minus 2, s minus 2. Okay, and then I'm going to multiply this one out. This is going to be s squared minus 5s plus 6. All right, and now I have a common denominator, so I can add on the plus 1. So I have 7, and then I can just get rid of this fraction here. All right, so now I have, so I'm putting everything over a common denominator. This is what we have. And now what I want is a partial fraction decomposition. So what would the decomposition look like? It would be equal to some constant a over s minus 2. The next term would be b over s minus 1 to the first power. And then the third fraction would be some constant c over s minus 1 to the second power. So this is what a partial fraction decomposition looks like for a fraction like this. So multiply, take this equation, forget the capital Y of S for now. The rest of this, multiply through by the denominator. So what you get is S squared minus 5S plus 7 is equal to A times, so it's, you multiply by all of this, so whatever factors are not present down below are the ones that, whatever factors are present down below cancel. So everything in this numerator that is not present down below, that is what stays. All right, so I have s minus 1 squared plus b times s minus 1 times s minus 2 plus c times s minus 2. All right, so what you have to do is find 3 distinct values of s, or choose 3 distinct values of s to substitute into this equation to be able to solve for a, b, and c. And you want to find those that are most convenient. Of course, the most convenient ones are ones that create zeros. So that'd be s equals 1 and 2. So first, substituting s equal 1. So I get 3 is equal to, so let's plug in s equal 1. That's going to go away. That's going to go away. This will still be left. So that's going to give me 3 is equal to c times minus 1. So c is equal to minus 3. So we get that right off the bat. Substitute s equal 2. So I get 4 plus 7 is 11, minus 10 is 1. And substituting s equals 2 will cause this term to go away and this term to go away. It'll just give me a. So that will give me 1 is equal to a times 1, so a is equal to 1. Now, there's no super convenient method to choose another s that will give you b, because there are only 2 distinct roots down here. We have 3 terms we have 3 constants to find. But you can just choose any other value of s. For example, I'll choose, say, s equals 0. So that's also pretty convenient. So I get 7 on the left side, and then I'll have a, which is 1, times 0 minus 1 squared, plus b, which is still unknown, times minus 1 times minus 2, plus c, which is minus 3, times 0 minus 2. So when I simplify all this, I'll have 1 from this part, and then I have plus 2b, so minus 1 times minus 2 is plus 2b, and then I have plus minus 3 times minus 2, so 6. Okay, so now I have 7 is equal to 2b plus 7. So if 7 is equal to 2b plus 7, so 2b is equal to 0, therefore b is equal to 0. So now I can rewrite the transform my solution. That's equal to 1 over s minus 2 plus this fraction is not there because b is 0. So I have minus 3 over s minus 1 squared. So now I can take the inverse transform, and then we'll be done. Okay, so y of t is equal to the inverse transform of 1 over s minus 2 minus 3 times the inverse transform. I'll make sure, I'm not sure if I said the right thing. Inverse transform of 1 over s minus 2 minus 3 times the inverse transform of 1 over s minus 1 squared. Okay, just by the linearity of inverse transform. Now I'm going to take into account the shift. Notice we have different shifts. Here we have a shift of 2, and here we have a shift of 1. So for the shift of 2, I'm going to have, that's going to introduce a factor of e to the 2t times the inverse transform of the unshifted function. You don't have to work it out this way, but I just want to show you where the individual steps come from. When you do enough of these, then you can just jump directly to this being, okay, the exponential. Okay, so we have minus 3 times, and here we have a shift of 1, so that's going to introduce the e to the t times the inverse transform of the unshifted function, which is 1 over s squared. Okay, and things that you have to have off the top of your head. Inverse transform of 1 over s is just 1. And then inverse transform of 1 over s squared is t. So finally, we can write down the solution. So it's e to the 2t minus 3t e to the t. Okay. All right, so that's the last example I have for today. So we've seen the procedure, same procedure followed each time. Use the rules for transforming derivatives to transform a differential equation. Both sides, keep it in mind if it's inhomogeneous especially, and you know, use a Laplace transform table that you want to have in front of you to transform whatever functions you have. Then do whatever algebra it takes to get the transform, Laplace transform of a solution. You want to isolate y of s. Then, depending on the problem, you'll do further work, like for instance, putting over a common denominator or using partial fractions. You want to get expressions like this, like 1 over a power of s or shifted s, or we saw in the third example where it's a completed square form. It's like 1 over s plus a shift squared plus a constant. Those kind of things transform back into exponentials, sines, cosines, or powers of t. So then you can get into a form where you can readily take the inverse transform, take a linearity into account first, take any shifts into account second. Then you have the simplest possible functions to, again, consult your table if you need to take the inverse transforms, and finally write down the solution, y of t. Um, Now, the homework will consist of certain initial value problems like the one that I've been solving. Other problems will just be working out individual inverse transforms, which is also involved in these problems, so it's sort of like a building block, if you will. So again, you want to have a Laplace transform table handy when you do these kind of problems. All right, so good luck with the homework for this section. It'll be due on Monday the 27th. So I'll have section 7.3 that's left to cover, where we'll deal with discontinuous functions and how we work with those to solve initial value problems, again using the Laplace transform. Something we weren't really able to work with before. So good luck.